Piotr for his excellent lecture. And it's my pleasure to invite our next speaker, Roger Amos from University of Technology of Sydney. And he will present us with his personal perspective on machine learning. So the title is Learning About Machine Learning. So please, Roger, give us that. All right.
I think this microphone's working, is it? Right, good. On the other hand, why can't I go backwards? Can't get my PowerPoint to page backwards and forwards. Oh no, the arrow keys are not working. That's what the problem is. Yeah, it's not. Key doesn't work.
Oh, something down there.
Ah, double click. Now that's a novelty. Right, here we go. Now it's entitled Learning About Machine Learning. And first of all, I'll point out that this is not solely my work, but it involves Rika Kobayashi, who is here, Marco, who is at the University of Technology, and 3 people from the Fujitsu company, whose presence I will explain shortly. But I'm new to machine learning, apart from a couple of small experiments. So I started in a completely different area, and I'm going to go back about 45 years and spend 3 or 4 minutes talking about how we got here. Now, when I started computing, machines were a lot less powerful than they are now. Because when I started, these machines in the red circle are machines with about 10 to the 8, 10 to the 9 operations per second. We are now up the top where there are about 10 to the 18. In other words, it has the power of the machine is a square of the power of the machine it was 40 years ago. Okay? Now, the machines there in that red dot include this machine in particular. That is the Cray 1S at Daresbury Laboratory in 1977. And that's where a lot of that happened to be installed in Britain just at the time I was starting to take quantum chemistry seriously. So that's the first real machine I used. And these vector machines were very significant in the history of computational chemistry because the computational chemistry programs are dominated by vector operations, or they can be if written properly. And so during the 1970s and 80s, there was an enormous amount of development done on computational chemistry programs based on these machines. And those developments are still all with us. It's not just the Cambridge program that I worked on, it's GAMES and Gaussian and MolPro and all of them. Those programs are all still with us. But of course, they changed. And after that machine, we got into slightly higher up, the massively parallel machines, up there somewhere. And the programs were all adapted. The word adapted is the important one, because what happened was they took the old programs and added MPI or OpenMP. And a bit further up, by the time we got to about 2010, GPUs were everywhere. And so the programs were adapted again by putting in language for CUDA or OpenACC, and they just kept going. Now, my point is that all these programs, which are now the legacy codes, are still with us. The computers have gone. Quite literally, that cray is a machine piece, a museum piece, because there it is in the Science Museum in London. And if you actually want to go and see it, there it is. If you're ever there in London, and that is the actual machine that I started most of my work on. There it is in the museum. I want to mention one more machine before I get to machine learning. And the machine I mention, your online audience won't see this, but it's this. Okay. That, according to Apple, has 10 cores. It's got a 16-core GPU, a 16-core neural engine, and theoretically, that does 10 teraflops. 10 teraflops. That is up about the point where the best machine in the world was in the year 2000. So do we believe this is equivalent to ASCII red or something like that? Well, the answer is no, I don't believe it, because it's not full 64-bit flops, it's 32-bit, and you'd need to get all these GPU components and neural engines working flat out to achieve that speed, and your chances of doing that are zero. However, this is the kind of machine exactly which is advertised as being suitable for machine learning. All this stuff, neural engines and things. So first of all, did I use it? No, I didn't use this machine at all. The only thing I used for this talk is I used this machine to write some Python code to do analysis of the results. So let's get to the actual machine learning part. Oh, what's happened this time? Going the wrong way. There we go. Right, it takes a long time for some reason. Here's a very, very simple workflow. They like the phrase workflow in machine learning. You get some data, you use some kind of recursion with a neural net, and you've got a model to put into your application. Now, depending on who's talking about this, for example, if you're the manufacturer of a machine like NVIDIA's, or if you're a mathematician or somebody who's interested in computer science, they'll have different emphasis on different parts of this thing. It's very slow changing. Not sure why this is. There we go. It's taking about 10 seconds to change a slide. Now, if you're NVIDIA or a mathematician, you emphasize that bit in the middle. It's all about the neural net. If you're doing chemistry, computational chemistry, and you want to do machine learning or chemistry or material science, in fact, it's not that middle section that's the important one at all. What does that do? Right. It's not that middle section that's important at all. It's the first one. Data, 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 data. That's what you need. And how do you get that data? Well, at the moment, we're getting that data by going back to all those legacy codes that I mentioned, all those old quantum chemistry codes. And the other thing that I've put in, another step which is sometimes de-emphasized, which is actually critically important, is descriptor. The descriptor is the thing that relates your data to the final application. The descriptor is the thing that's optimized by that neural net. Now, if you go back to molecular dynamics, classical molecular dynamics, and you want to get the force field of a complicated molecule, your descriptor is the bond lengths and angles and dihedrals, because the entire force field, and there's the amber force field at the bottom, is written in terms of that, which is fine, enormously fast, but it's also not as accurate as you really want. So we'll go to machine learning for force fields, and we're using the DeepMD package. There are other packages which analyze results and get you a force field. And what this is in terms of You see this thing at the bottom, dij. It's a function of 1 over the distances between the atoms. And the total descriptor is not just the dij for the interaction of atom I with atom j. It's a function of all, I should do the word functional actually, it's a functional of all the dijs for all the atoms within a given radius. And that radius is 7 or 8 angstroms. So there could be 20 atoms in there. So instead of just having 2 or 3 atoms like the amber force field, this thing's going to have 20 atoms interacting with each other. And so what you do is you take your forces and your energies as produced by some ab initio program, and you feed it into the machine learning program. And what comes out after the neural net has found the functional relationship between these dij objects and the forces, what comes out is a force field understandable by the LAMPS program. So how did we get to this point? Now, there were some people from the Fujitsu company back on my introduction. They were involved. They were involved because they actually contacted us, that's Rika and myself, to ask if we could explain how to do machine learning for force fields. And they wanted an example, and they wanted something that they could do themselves. And they actually started doing this, and we kept going. Now, what happened was that Marco Franzi, the other person on the author list, took some geometries for gold 20, not just one like the equilibrium, but these other ones are approximations to excited states, but they're a long way off. In other words, we're not starting at the equilibrium because we deliberately wanted non-equilibrium structures. And he ran a long machine molecular dynamics calculation with the VAST program on all of these structures. And you feed it into the learning. And what comes out is something quite sensible. What you get is that the energy is reproduced with an error of about 1 part in 1,000. That's quite good. The forces, well, this is the one on the left is the ratio between the calculated and the machine learned force. Now, in an ideal, that ratio would be 1. You can see it's strongly peaked at 1. And the angle between the calculated and the machine learned force should be 0. And you can see it's strongly peaked about 0. So that's promising. Good. So when you use the force field, you get on this degree of resolution on these pictures, the VASP one, the VASP structures, the LAMP structures look identical, completely identical. If you examine them in close, you'll find some very slight differences in bond lengths, but not worth walking about. It's also true from excited states. You can get VASP and LAMPs to agree. Now, this has been published a month or so ago, and you can look it up. The paper also contains details of the actual molecular dynamics runs, which I'm not going into, because what I want to ask is, what's the point of just doing gold 20? That's small enough that you can run a full ab initio force field without mucking about. So can we use the potential we've just derived for other systems? So I tried it on gold 30. And on the left-hand side is the VASP structure for gold 30, the proper equilibrium. And the one on the other one is the structure obtained with LAMPs using the potential for gold 20. And that's not too good, is it? But if I just expand it a little bit, what I did was I took gold 28, did a simple geometry optimization, which is only about 40 energy evaluations. I stuck it into the training set, and now gold 30 agrees perfectly. And note that gold 30 is not in the training set. when you have lots of data like this, you divide it into training sets and validation sets. Gold 30 is the validation set. It wasn't actually parameterized, but there it agrees nicely with the VASP one. So let's keep going. This is gold 55. One of the structures are gold 55s. There are several different ones. Again, we had to do one geometry optimization and add about 40 or 50 energies to the potential we had for gold 30, and they agreed perfectly. This is gold 58, and we didn't have to change the potential again. In other words, this is a validation calculation, not a training one. So the same data set, the same potential, got us the geometry of gold 58. Let's keep going. This is gold 147. 3 different structures, all high symmetry. And I haven't specified them as being LAMP structures or VASP structures because you can't tell the difference of these pictures. And importantly, I didn't have to change the potential again. The potential I had got to get as far as gold 55 worked perfectly for this lot. So what we're learning here, what we're learning, yes, I'm getting close to the end. What we're learning is that we learned how to do machine learning into atomic potentials, and we showed the people at Fujitsu that we could. What we learned was that you need an awful lot of ab initio data currently calculated with the standard legacy codes, because there isn't really anything else that's robust enough to do them. You can do fitting. We used DeepMD, but there are other codes. And we produce the potential, which goes straight into LAMPs and reproduces the original data. We learned that the potential developed on one system can be expanded to larger systems with relatively little extra data, which is important because calculations on VASP or Gaussian we could have used or anything. These are relatively expensive calculations. And so if we have to stick a lot of extra calculations in, we're not really winning. Okay, but this we've shown that it can be expanded. And let's finish with a couple of little words of caution. These examples have been successful, but we will note that the calculations on gold 147 were restricted to high symmetry cases because we found some approximate structures which somebody had proposed, and these were structures that were just obtained by making quite literally geometric shapes from solid gold. Okay, so they weren't optimized or anything. They literally just produced some shapes which they cut up solid gold in various patterns and got little nanocrystals. But right, they were all high symmetry though, but we did do them. We successfully optimized the geometry properly with VASP and LAMPs, and they agreed. Now, however, larger systems like gold 147 are strongly suspected of having an amorphous structure, i.e. they're not regular crystals, and those may be lower in energy. And I can't prove that yet. And I can't prove that because our molecular dynamics person, Marco, is currently running MD calculations using our potential to see if he does it at elevated temperature, we get amorphous systems. Now, at that point, we might finally be gaining on all the computer time we use to parameterize the potential, because he's going to be using tens, probably more, more than tens of thousands of points in an MD thing. It's probably 50 or 60,000 points on each structure. And that is no longer trivial, even with LAMPs, okay? So eventually we will exceed the point where all that calculations with VASPs were the dominant factor. But we haven't got there yet, and so there's a potentiality for another talk sometime in the future. So thank you again for listening. Thank you for the organizers for inviting me, and I hope you all enjoyed that. Thank you.
Thank you very much, Roger, for a very nice presentation. And now your talk is open for discussion. Please, Alfie.
Maybe you have to repeat my I'm not connected to the internet. So very nice talk. We are using mostly machine learning for graph design. And currently there is a debate because normally people go for a lot of data in the text. But we think maybe we should less data, but more qualitative, high accuracy data we could gain. So what would you say is here?
Okay, thank you. The question for anyone who didn't hear it is basically, do we have to use all that much data or can we get away with less? And the answer should be, yes, we could do the parameterization with many fewer points. We started with a full molecular dynamics calculation on Gold 20. That was 20,000 points. You really should be able to do it with a few hundred. And there are techniques in the literature where you start with a small amount of data and expand it by a learning process. You have to test every time your potential has taken you out of the parameterized area, because you can't trust any potential to go outside its learned area. So you start with a small number of points, and every time your prediction is outside that area, you have to stop, get more points. And that may work. You might be able to do all this with less than 1,000 points. Okay? And then hopefully it's like what we've seen. If you want to do a different system, a different but related system, you just add a few extra points. Hopefully. I can't prove that, but it's in the literature and people have claimed that.
All right. Thank you, Roger. And our next question goes to Piotr. Piotr?
Hi, Roger. Very nice talk. Very impressive, actually. But
Thank you.
Let me ask you a question. I haven't dealt in my life a lot with gold. I dealt with small gold clusters. The largest was gold 8. And I know about gold 8 that within a few kilocalories per mole, you may have several structures. How difficult is for you to distinguish between different structures that differ by a few kilocalories per mole?
Right. Yes, a gold cluster has many, many local minima. For gold 20, the answer is easy because there's a very, very symmetrical structure. For the other ones, it's not easy. And I am not convinced yet that the machine learning potential would correctly order all of them, although it seems to be capable of finding the global minimum for each of our nanoparticles. But if we looked at alternative structures, I'm not convinced it would have them all in the correct order. So I think if it was me doing it, I'd do what they do with ab initio calculations. I'd optimize it and then do separate one-off calculations on all the alleged minima to see which order they really should be in. You probably can't do that with a protein. So by the time you get to really big systems, you're not going to have much choice. You're just going to have to believe the force field.
Okay, thank you very much.
Any other questions from the audience? All right, if there are no more questions, let's close this session and thank all our speakers of the first session for their very nice presentation. The next session